Okay. Please, if you ask your question.
Mr. Young,
Hello. I'm listening.
let's start this one again. Why did you define the this side, the density times the volume by the mass of the apparent weight?
Come again.
Why did you divide the density times the volume by the mass
No,
of the apparent?
no. I'm not dividing. I was trying to explain to you that. Oh, thanks for the. I was trying to explain to you that rho v is mass of fluid display. Okay, I was just trying to let you know that rho v. See, density is equal to mass over volume, right? So when you make mass the subject, you have rho v. So I was just explaining to you that this rho v is rho L, V L, S. Let me use L instead of L. Mass of fluid display. Are you okay?
Yes, please.
Thank you. Thank you for the
Mr.
appreciation. Yes.
Mr. Bia, please, I was saying that please can you go over the tension part. I
Okay.
didn't get that before.
So this is what I'm saying. The mass is suspended on a spring. The mass has or exerts a weight given by its mass times gravity. Now, when there is vertical equilibrium, and with vertical equilibrium, what do I mean? I mean that, you see, there is no motion along the vertical plane. The weight of the object is balanced by the tension within the spring. So, under vertical equilibrium condition, we are saying that the tension T in the spring, tension T in the spring is balanced by the weight mg of the body. And so we are saying that T is equal to mg. So if you suspend a body on a spring and the weight is not falling off, or the mass is not falling off, then it implies that the tension in the spring or the thread, if it's a thread, is equal to the weight of the body suspended on the spring or the thread. Hence, T is equal to mg. Class, are we fine?
Yes.
Then I'm giving another scenario. And the second scenario is that the same setup is suspended. This time, the mass is submerged in liquid or water. So I'm submerging the same thing. Please let me change my marker, okay? I'm submerging the same thing into a beaker of water or any other liquid. When you submerge this in water or liquid, yes, there is still a tension T within the spring. So we have T directed to where we have the support. Plus, what are the forces apart from the tension in the spring? what other force exists in around or in the whole system?
Cohesive force.
And apart from the tension, what other forces exist in a system? Yes.
Cohesive force.
Adhesive.
Um,
Force.
adhesive force by
Upthrust force.
good. No, we don't say upward force. So the word thrust is a
Upward
force.
force.
Yes, the word thrust means a force. So upthrust means upward force. Okay.
Force.
So we have the upthrust produced by what? Produced by
The
what
objects in water.
So what produces the upthrust?
The displacement of water.
So
The weight
specific-
of fluid displays.
Yes, I understand, but what actually produces the upthrust?
The mass.
No,
The weight.
no.
Density.
The immersion.
The water.
It's the water or the fluid. Okay, so class upthrust is a force within fluids. And when we talk about fluids, we are talking about anything liquid or gaseous. So upthrust is a force produced by fluids, which can be liquid or gases. That is why we say that it depends on the density. The lesser the density, the lesser the density of the liquid. Finish
The
it.
less after.
The lesser is the upthrust. Is that good? So we have produced by a liquid. You. What other force exists in the system? What other force exists in the system here?
Weight.
The weight of the weight of the object.
Object.
Good. mg. Now let's look at the total forces in the upward direction and the total forces in the downward direction. What do we have acting upwardly? Yes.
Upthrust.
So we have the
Okay.
upthrust acting upwardly.
The weight of the body.
So
Tension.
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 tension in the string. And then what and what? Okay, forces act downwards.
The
Weight.
The
So
weight
we
of
have
the body.
weight mg. Okay. Now once the system, when suspended in liquid, stays in equilibrium, then it means the total upward force is balanced by the total downward force. So once there is a vertical equilibrium, it means that U plus T must be equal to mg. Let's make T the subject. Class, hello.
Please, can you explain the U plus T from that side? I didn't get it.
Agusha, I got it. Oh. If you didn't get it, I got it. Okay, Agusha, we are looking at the total forces acting upwardly and then the total forces acting downwardly. Okay, if you look at it, we have T the tension in the string going up, it is always directed to where we have the support, the point of support. We also have the upthrust as another force going upwardly. So we are summing up all the upward forces. That is sum of upward forces. And then this is the only single the downward force. Now, once we have the system being in equilibrium, okay, when you suspend, once this weight is small, it will never drop, okay, from the spring balance. It will be in equilibrium. Then it means that total upward forces must be balanced by the total downward forces. Akosu, are you okay?
Yes, please. Yes.
Good.
Thank you.
So let's make T the subject. Let's make T the subject from here. Yes.
mg minus u.
So T is equal to mg minus u. What it implies that if you suspend a body in fluids and you are looking for the tension in the spring or in the string, either the tension in the spring or in the string, it means that the tension is given by the weight of the body minus upthrust. Then the weight of the body minus, let me write it simple, weight of body minus upthrust is equal to the tension in the spring. Either the tension in the spring or in the string. Class, are we fine?
Yes.
Yes, please.
Let's also make a comparison. You see, we said upthrust is equal to weight, real weight minus apparent weight, which is weight in liquid or fluid, is equal to what? And this is equal to U, which is the upthrust.
Yeah.
Let's make the apparent weight the subject. Let's make the apparent weight the subject.
It is equal to u minus L.
Open your eyes.
U plus
And the real weight minus the
So this is W minus U, isn't it?
Yes.
And what it means is this is also tension is equal to the same real weight. So it also means that in calculations, the apparent weight is also equal to the tension in the string or the spring. The apparent weight WL is also equal to the tension in a spring or string. So when the question demands that you find the tension in the string, finding the apparent weight is the same as the tension within the string from these two considerations. Are we okay?
yes.
Yes.
Okay, we are going to solve a question. So, hello. Let's solve a question. Please, I'm coming. I'm trying to extract the question. Are you ready? Okay. A piece of aluminium, with mass 1.00 kilogram and density 2,700 kilogram per cubic meter. A piece of aluminium
Mr.
with
Dear.
mass, hello.
And please, can you begin?
A piece of aluminium with mass 1.00 kilogram, 1.00 kilogram.
Mr. Dear, please can you start again?
Hey, I'm still here. I haven't even moved. So, a piece of aluminium with mass 1.00 kilogram and density 2,700 kilogram per cubic meter. And density 2,700 kilogram per cubic meter is suspended from a string. Is suspended from a string and then completely immersed in a container, of water, Calculate the tension in the string. A before and B after the metal is immersed in the liquid. B after the metal is immersed in the liquid. So, two quick questions. Okay. Class, okay.
Yes.
Okay, so I'm giving you about 4 minutes to try. Okay.
Okay.
I'll be with you. The density is 2,700 kilogram per cubic meter, and it's suspended from a string and then completely immersed in a container of water. Calculate the tension in the string before and B after the metal is immersed. So the A part, okay, says that we calculate the tension before. And from what we were doing, we realized that when an object is suspended on a string, okay, the tension that exists, okay, in the string or the spring, when it's the mass is in open air, is given by T is equal to the weight, which is mg. The tension, therefore, will be equal to the mass, which is 1.00 times gravity, which in most cases is 10. So this will be 10 Newton. So it means that the tension in the spring when it is weighed in air is this. Are we okay? Are we okay?
Yes, please.
Usually when the mass is given in grams, then you have to either convert the mass in grams to multiply by 10, or use whatever they give to you in grams and multiply by 0.01 Newton. Then you have the same thing. Okay. All right. So the B part. What is the tension when it is suspended? The mass is suspended in water. To help you, okay, get this thing without learning the formula by rote, all that you have to do is that when it's suspended, immersed in water, updraft will be in the same direction as the tension. So T plus U would be balanced by mg. Therefore, the tension will be equal to the weight minus the updraft. Okay. What is the weight? The weight will certainly be 10 Newton minus updraft. Updraft is always given by density of the fluid. Updraft will be given density of the fluid times volume of fluid displaced times gravity. Okay, so we have 10 Newton minus what the density of the fluid. The density of the fluid displaced is water.
3,000.
Duvio, come in. Duvio.
So I was coming. So what if you first find the volume of the fluid before you
Okay, so let's go systematical, okay? Because it's a good question. We have to updraft is equal to rho Vg, where rho is the density of the fluid. Please, what is the density of the fluid here?
2,700.
2,700. Any different view as to what the density of the fluid is? Hello? Any different view? But let's go into the question to understand the kind of fluid they are talking about. What was the fluid?
Water.
You see, the fluid is water. And so here we use the density of water, which in gram per centimeter cube is equal to 1, but in kilogram per cubic meter is 1,000. Class, are we okay?
No, please.
And over here, we have to use the density of water in kilogram per cubic meter because all other units are given in SI units. Look at the density of aluminium. The density of aluminium is given as 2,700 kilogram per cubic meter. The mass of water is given in kilograms. So the density of water must be stated in kilogram per cubic meter. So 1,000 times. Now, what's the volume of water displayed? What's the volume of water displayed?
0.
Yes.
4.
Pardon? Let's share ideas. What do you think will be the volume of water displayed?
0.001.
0.001. Why? Why? And why? Okay, time. You see, let's go to hiatus. When you were doing that experiment in determining the density of irregular objects, you tied an object to a string. You denoted an initial volume V1. Then the object tied to the string was gently lowered into the measuring cylinder. Okay. Then you took note of the final volume after the rise in the level of water, V2. You determine the final the volume of water displaced by subtracting the initial volume from the final volume. Okay. What you are doing is that when a body is completely or totally immersed in fluid, the volume of water displaced would be equal to its own volume. If I am dropped completely in water or in pool, okay, in a pool, the rise is equal to my body volume because I am completely immersed within the fluid or the water. Please, are we okay?
Yes.
In the same way, if I use one leg to step within the pond, there will certainly be a rise. So the rise is also equal to that part of my body which stepped into the water. So the rise in the level of water is equal to the volume of my leg, that part of my leg which got into the water. So volume of water displaced is always equal to either the whole body of the object or part of it. So once the question talks about the metal, okay, completely submerged in the water, Asumani, what's the problem? Asumani, quick one. What's your difficulty here? Oh, let's be quick about
The part where the 1,000 came from.
the
Part where the 1,000 came from.
Oh, you see, density of water is equal to in gram per cm cube is 1.0 gram per centimeter cube. Okay, if you convert 1 gram per centimeter cube into kilogram, the same thing will give you a density of 1,000 kilogram per cubic meter. If you want, let's convert. So class, we are learning. So we have a density of 1.0 gram per centimeter cube. Okay. Now let's convert the numerator, which is in gram to kilogram. We know that 1,000 gram will be equal to 1 kilogram, isn't it?
Yes, please.
Good. So what will be one gram in kilogram? And look at something, a systematic way of converting this. You see, 1,000 gram is actually 1,000 by 1 gram, isn't it? 1,000 gram is 1,000 times 1 gram, right? So if I'm looking for 1 gram in kilogram, all that I do is to divide both sides by 1,000. So this and this will cancel. So I have 1 gram is equal to 1 times 10 to the power negative 3 kilograms. So class, it means that 1 gram is equal to 0.001 kilogram. Are we okay?
Yes, please.
Okay. Then let's come to the denominator. So we have 1 gram per cm cube, which is equal to 1 gram divided by 1 centimeter cube. And so we've converted the numerator. We have 1 times 10 to the power negative 3 kilograms. Let's convert the denominator. We will do this by using the prefix centi. The prefix centi means 10 to the power negative what? 10 to the power negative 2. Please.
Miss Taylor, please can you adjust your screen?
The prefix centi, this means 10 to the power negative 2. So we are substituting 10 to the power negative 2. M is still there. All raised to the power 3. We are raising everything to the power 3. Because of this power here. Class, are we okay?
Yes.
Good. So when you do this, you have 10 to the power negative 3 kilograms divided by 1 times 10 to the power negative 2 all raised to the power negative 3 is equal to 10 to the power minus 6